A vertical plane wall holds back a pool of water, density of 1,000 kilograms per cubic meter, which is 1.5 meters deep. The wall has a triangular gate in it that is hinged along the bottom edge and held closed by a horizontal force F applied at the top corner. Calculate the force F required to hold the gate closed. So here's our pool of water, 1.5 meters deep. This is the gate, and here we're looking at it in cross-section, so we're looking at the edge of the gate. There's a hinge down at the bottom here, and a force here holding it closed. So if it wasn't for this force, of course, this gate would flip open and the water would come rushing out. Notice the direction of G is also given in the diagram. We also have a second view here, so if we look at view AA, which is looking at this thing from the side, we see that the gate is triangular. So the hinge is along this bottom edge, and the force F is applied up here at this spot. So we can use this diagram as our given information, because essentially everything that's given in the problem is shown on this diagram. So we'll start off by writing down what we're asked to find. And what we're asked to find in this case is just the force F, shown on the diagram, so that guy right there. So we need a list of assumptions. And we'll be filling in these assumptions as we make them later on in the analysis. So I'll start my analysis here. And the first step in any of these types of problems is to think about the static equilibrium of this gate. So we have an object here, a gate, with a bunch of forces acting on it, and it's in static equilibrium. So the way we can usually calculate those forces is by looking at a free body diagram of the gate, and that'll really help us develop a solution strategy to come up with that force. So here's my free body diagram of the gate. And this is usually the first step in these types of problems. So I'll show the gate here. So that's the gate. So there's a force pushing at the top edge of that gate. That's what we're looking for. Down at the bottom is a hinge. So there's going to be some reaction force in that hinge. And I'm just going to call that R. And I'm not too concerned right now about the direction of that force. So this vector R just represents the fact that there is a force acting at that point. So that's a reaction force in that pin. Now, of course, on the left side here, we've got fluid acting on this, and I'm going to represent the effect of the fluid on this gate by a force and a moment. So the force that the fluid exerts on the gate and the moment that the fluid exerts on the gate. And I'm applying those at the hinge point. So I've essentially predetermined here that I'm going to place the origin at that point. So when we take a look at this, that's what we're trying to find. And so if we take a sum of moments around this hinge, then there's going to be two things involved in that sum of moments. The moment that the fluid is producing and the moment that this force is producing. And those have to add up to 0 if this thing's going to be in static equilibrium. Notice the reaction force in the hinge doesn't come into it because regardless of what direction that thing acts, it goes through that point and so has 0 moment around that point. So that's the basis that we're going to proceed on. So I want to go back up to our diagram here and show our coordinate system. So that's where the origin of the coordinate system is going to be. I'm going to put the x-axis in this direction, and I'm going to put the z-axis in this direction. So x to the right and z straight up. You can choose any coordinate system you want, any pair of Cartesian coordinates. You could have it pointing this direction if you want, down, it really doesn't matter. It certainly does make sense, however, to have one of our coordinate directions along the surface of this gate. And for a vertical gate like this, that makes sense as well because we want z pointing straight up. Notice that this particular gate is not tilted. Some of the questions that we come across, the gate is tilted. In a case where the gate is tilted, it's a lot easier to do these problems if you also tilt your coordinate system so that one of your coordinate directions points along the surface of the gate. But this one's vertical, so it's we just use a vertical coordinate system. So based on this sketch, the approach to this problem is going to be that the sum of moments around the origin must be equal to 0. So notice this is a critical first step in these problems. Before we do any of the fluid mechanics, calculating any of the forces or any of the moments, we got to recognize that the approach to this problem is going to be a sum of moments. Now the other thing I want to point out here is that I've chosen to represent the effect of the fluid on this gate by a force and a moment. So I apply that force at the origin and I apply the moment at the origin. Okay, that's the equivalent force system that I've chosen to use to represent this. So notice the other thing here. We're not actually going to find this force. So even though we're looking for a force, the force to hold this gate closed, we don't jump in right away and find the force the fluid exerts on the gate. We can't get this force from a summation of forces because we don't know what this is either. But we can get this force from a sum of moments because this reaction force is not involved in the sum of moments. So that's a key to these problems, is recognizing at the beginning here where we should be spending our time. So, like we said when we introduced the free body diagram, there are two things contributing to this moment. The moment of the fluid pushing on the surface, plus the moment due to this force at the top. And I'm going to represent that moment by R cross F. And those have to add up to 0. So the R here is the position vector to where that force is applied. So we'll talk about what that is later on when we get to it. So let's spend our time now figuring out what this moment is. And this is where the fluid statics that we've been taking comes in. We have an equation for this moment. It's the integral over the surface of R cross N P dA. This is always our starting point for calculating the moment due to a fluid on a submerged surface. So the approach we're going to take is we're going to look at everything inside of this integral and figure out what it is. So I'm going to start that over here. First of all, position vector. Take a look at our diagram. So we're talking about a little element of area on there, dA. What does a position vector look like that tells us where that is? Root is at the origin of the coordinate system. Tip is at our element of area. So notice that particular vector is pointing up in the z direction. Its magnitude is simply z, and its direction is k. So the position vector here is zk. Next thing we need to figure out is the unit normal. So again, we go back to our diagram to see what a unit normal looks like. And remember that a unit normal projects into the fluid. So if we consider our same little dA here, unit normal is going to look like that. So in the coordinate system that I chose here, that unit normal is in the negative I direction because I've got x pointing to the right, unit normal pointing to the left. So the unit normal in this case is equal to minus I hat. Next thing we can do is take that cross product. So R cross N is going to be equal to minus ZJ. So just taking ZK crossed with minus I, we get minus ZJ. So notice this is what gives us the direction of our moment, the J. The next thing we see in our moment equation is the pressure, and that's going to come from the basic hydrostatic equation. So the starting point is rho G minus A. And as soon as we write down our basic hydrostatic equation, we should go back here and say fluid is in a hydrostatic state. So we can't use that equation unless we make that assumption. The other assumption we should have in our list here is an assumption we made right here. We said that all of the moments acting around this origin are the force and the fluid. Well, that assumes that this hinge is frictionless. So we should have that in here. So it is a frictionless hinge. So go back to work with our basic hydrostatic equation. Assuming that this thing isn't accelerating, we set the acceleration to 0. So I'll go back here and say acceleration is equal to 0. Certainly should be the case here. We recognize what g is in this coordinate system, and it's minus gk. So we only have a k component on the right side, so we just extract the k derivative of p from the left side. So out of this vector equation, we get a scalar equation, dp dz is minus rho g, and this tells us that pressure is minus rho g z plus a constant. So we integrate this to get that. So the constant of integration in this is important. Remember, to figure out the constant of integration, we need to know some point where the pressure and z are both known. So we go back and look at our diagram. When z is equal to 1.5, which is right there, the pressure is equal to 0, because that's the surface of this water. So that's the condition we use to get that constant. So we say at z equal 1.5 meters, pressure equals 0. So we take this and substitute it in there. We take this and substitute it in there and solve for c. So 0 equals minus rho g, and I'm going to put this number right in there, 1.5 plus c. Therefore, c is equal to 1.5 rho g, and this 1.5 is in meters. So we'll keep everything in basic units here. So our expression for pressure then, we can go back to this and rewrite it with this c in it. So that P equals rho g 1.5 minus z. So that's our equation that gives us pressure as a function of z. The last thing we need in our expression for the moment is dA. And again, take a look at our coordinate system. This element of area lies in the ZY plane. Remember, the y-axis for this particular coordinate system is going to go directly into the screen. Okay, so that gate is lying in the YZ plane. What I should do is go over here to this view and show the coordinate system on there as well. So that's Z, and this is Y. So the gate is lying in the YZ plane. So an element of area is dy dz. So go back down and state that. So the last thing we need here is dA is dy dz. So now what we should do is take a look at the limits of integration. So I want to go back up to this sketch, and we'll take a look at this view of it because we can see our gate. Notice in the z direction, we're going to be integrating from z equals 0 up to z equals 1.5. Remember over here that the water only goes up to 1.5, so if I continue this on over here, the water level is right there. So in the z direction, we want to integrate from 0 up to 1.5. There's no water on this last little bit, so we got to stop right there. So the limit of integration on z will be from 0 to 1.5. Now in the y direction, this limit of integration is a little more complicated, and this is where the triangular shape of this gate comes in. Notice in the y direction, the limit of integration is going to be from 0 to there. If we're up here, it'll be from 0 to there. So the limit of integration on the y is actually a function of z. So let's take a look at what that function is, and we'll just do that right here, or we're close to the diagram. So at z equals 0, the width of this gate is equal to 1. Okay, so down here at z equals 0, the width of the gate is 1. And at z equals 2, so up here at the top, the width of the gate is 0. So we can write an equation for the width of the gate as a function of z based on these 2 points. And of course, it's a linear equation because that's a straight line. So that equation will be the width of the gate is equal to 1 minus z divided by 2. Now let's just make sure this equation works by taking a look at the two endpoints. Well, when z is equal to 0, down here, the width is equal to 1, and that's correct. Also, when z is equal to 2, put a 2 in there, we get 1 minus 2 over 2, the width is 0, which is true at that point. So this equation gives us the width as a function of z, and we need to use that as an upper limit of integration on the y integral. So now we're ready to assemble our whole integral down here at the bottom. So the moment that the fluid exerts on this surface is equal to negative integral, and in the z direction we'll be integrating from 0 to 1.5. In the y direction, 0 to 1 minus z over 2. So this is a critical part, and this is what gives this gate its triangular shape. The limit of integration on y is a function of z. R cross n is minus zj. The pressure expression is rho g 1.5 minus z. And our element of area, dy dz. So that's everything that we've talked about here pulled back into our moment. So this first integral from 0 to 1 minus z over 2 of dy, notice nothing inside of here depends on y. So what we can do, in addition to taking the constants out front here, we can do this first integral with respect to y right away. Okay? So we have the moment. Notice I have a negative sign here and a negative sign here, so I'll let those annihilate each other. We have rho and g that are constant, and we have j that is constant. So that can all come outside of the integral sign. Still have our z integral from 0 to 1.5. We still have what's left of our pressure expression here and a z. So I'm going to distribute that z into this, and I'm going to write this actually as 3z over 2 instead of 1.5z minus z squared. So remember a z there, multiplied by that z gives z squared. Now, since we've finished our y integral and nothing in here depends on y, that just evaluates to 1 minus z over 2, and then of course we still have to integrate in the z direction. So next thing we need to do is distribute these two terms out. So still integrating from 0 to 1.5, haven't done that yet. Multiplying these out, we get 3z over 2 minus 3z squared over 4 minus z squared plus z cubed over 2 dz. We can combine the two terms here that are based on z squared. Get rid of one of those terms. So we have rho gj still. Integral still waiting to be done. We have 3z over 2 minus 7z squared over 4 plus z cubed over 2 dz. So now we're ready to actually do the integration. Rho gj still out front. This becomes 3z squared over 4 minus 7z cubed over 12 plus z to the 4th over 8. And that's going to be evaluated from 0 to 1.5, which is just 3/2. So this is rho gj times 3/4 times z squared, which is 27 over 8, plus 1/8 times z to the 4th, which is 81 over 16. So the density we know, 1,000 kilograms per cubic meter. G we know, 9.81 meters per second squared. And of course this is all a number we can evaluate. So we calculate this out, and it comes out to 3,448.8 J Newton meters. Notice there's still a J in there. That's coming from here. And that's what gives us our direction. So that's the moment due to the fluid. So let's just jump up to our picture again, or our diagram again, and make sure the sign of this makes sense. So this is a positive J moment. Come up here, of course this fluid is going to be trying to turn this gate in that direction. And that's the positive J direction. Okay. Notice the J unit vector is pointing into the screen. So that's positive moment. So that makes sense. So now what we need to do is we go back to our summation of moments here. We've figured out a number for this, and we're trying to find that force. So we'll go back down to the bottom and start working with that. So we'll go back to our summation of moments. We put a number in for the moment that we just found. 3448.8 J Newton meters plus, so that's our moment due to the fluid, plus R cross F. That has to equal 0. So what is R? Go back up to the diagram and take a look at what this is. So this force is being applied at that point. So R is a position vector for that point right there. So its root is here. It has a magnitude of 2, and its direction is K. So R is equal to 2 meters in the K direction. So we'll rewrite this equation, substituting that in. So we have 2 meters in the K direction crossed with F is equal to, bring this over to this side, is equal to 3448.8 minus J Newton meters. So notice the negative sign, by taking this over the other side, I've attached to the direction here, minus J. So take a look at this. K, if we just think about the direction of these things, the magnitude is going to be just 3448 divided by 2, that's all fine. But K cross what is equal to minus J? Well, that's where the direction of our force comes from. So the force, its magnitude is 3448.8 divided by 2. Remember this 2 here. Units of that is simply going to be newtons, because we have Newton meters divided by meters. And the direction is going to be minus I. So K cross minus I is equal to minus J. And so that force ends up being minus 1.72 I kilonewtons. So let's just make sure that sign makes sense. So if we go back up to the top here, this force is in the minus I direction. Remember, our X is that direction. So it makes sense that that force is in the negative I direction. So the final answer there is that the force is negative 1.72 I kilonewtons.